All right, hi everybody. I'm Paul Jeffries from Rambol, and I'm back here again for Parametric Engineering Week 7. And this week, what we're going to be doing is looking at using Grasshopper and a part of it called Galapagos for optimization. And in particular, we're going to be looking at a family of optimization algorithms known as genetic algorithms, so called because they kind of mimic the process of evolution by natural selection. And one of the nice things about Grasshopper is it has a means of doing this built into it. So what we're going to be looking at is Galapagos. It's part of Grasshopper, written by David Rutten himself. It's nicely integrated with it. You don't need to worry about plugins. You don't have to go for any big faffy setup or anything like that. And what we're going to be using it for today is to look at and solve and optimize a problem. So far in this course, what we've mainly been doing is showing you a particular type of geometry and then showing you how to use Grasshopper to generate that type of geometry. But generally, the way that we tend to use Grasshopper in real life is when we've got some kind of problem that we want to solve, and we use Grasshopper to actually work towards a solution to that problem. So we leave playing with the fancy geometry often up to the architects. Our job is then to sometimes generate that geometry and to derive structure for that geometry, but also to try and rationalize it, to try and give it some rigor, to try and put some engineering judgment behind it. So the problem that we're going to be looking at today is a very common one in structural engineering. It is how do you set out your column grid to support a building. So as I'm sure you're aware, we generally like to have regular grids of columns as part of our design. It helps to keep things standardized. You can have standard lengths of elements. You can make the set out nice and easy for all the kind of other disciplines that you need to coordinate with. And it also makes the process of design sometimes a bit easier. So where we can, we like to keep a regular grid of columns. We can't always achieve that, of course, depending on the geometry. And sometimes we have non-orthogonal geometry, and we still need to be able to kind of take account of that and work with that and try and fit a grid into that geometry. So that's what we're going to be doing today. There is a base file for this session. The link was up there earlier. If you missed that, here it is again. So try and download that file if you haven't already. And what we're going to do is we're going to treat this as being a floor plate or a building footprint that we've received from an architect, and we then need to impose a structural grid onto that. So sometimes architects themselves will actually have a grid arrangement for their architectural layout. Sometimes they won't. Sometimes you'll have to try and impose one on that for them. So hopefully everyone's got this file by now. I'll give you a few seconds just to get it if you haven't already. And what we're going to do with this is we're going to take that surface. We're going to use Grasshopper to set up a plan arrangement of columns following a regular grid. And then once we've got that working, once we've used Grasshopper to create all our column positions and set that out, we'll then be using Galapagos to try and optimize that arrangement and try and come up with an optimum column arrangement for this particular building footprint. So if you go to that link, you should find a file like this in there. So all this file has in it is just this one surface that we're going to be using as our base input. So open up that file, type in Grasshopper, and then first thing we're going to do is to bring that surface in. So this might be the kind of arrangement that you've got from an architect. He might send you a CAD file or something like that. with this arrangement in. It's not too uncommon that you would receive something like this and then have to work from it. So first of all, we'll bring that surface in using the surface parameter component under params geometry. So as we've done many times before now, we'll drop one of those down. We will go to display and put draw icons on. And then we'll right click on that, go to set one surface, we'll select that surface. Everything that we're going to be doing today is in plan. We're not going to kind of complicate this by going into 3D, although you may wish to do so afterwards if that's something that entertains you. We're going to keep everything in plan, so I'll just put this into top view so that we can just see this surface here. So this represents a building footprint with a slightly irregular outside facade line, and then a big hole in the middle of it, which maybe is an atrium, maybe it's a set of escalator spaces or stair spaces, or possibly a service hole. A lot of the time you'll have to deal with penetrations through your slab like this and adjust your structural arrangement to fit around stuff like that. So this isn't too ridiculous a shape. It represents something that you might come across in reality. And what we'll do is we'll generate a regular column grid on top of this. So has everyone got that file now? Can I make this full screen? I'll take that as a yes. So what we'll do is we'll set up our grid. And to control our grid, we're going to want to set up 4 basic parameters. We're going to want to have the spacing of our grid in the x direction, the spacing of our column grid in the y direction, and then also a position of that grid in 2D space. So a kind of a start point to that grid relative to the origin there, so that we can move that whole grid around and fit it within this region. So we're going to have 4 basic parameters for that. The first one is going to be the grid origin x coordinate, and we'll use a slider to control that. So we're actually going to create 4 sliders here. So we could create that slider by clicking up here in input, dragging down a number slider, right-clicking on it, going to edit, setting that up. What we've shown you before is a shortcut where you can just type in a number followed by a few decimal places and get out a grid that way. There are also a few other ways of setting this up. So I don't know if we've shown you this already, but one way you can specify both the starting value of that slider and also the minimum and maximum values of that slider is to, for example, type in a starting number that you want to come from, and then put a lesser than symbol, and then put the initial value of that slider. So in this case, I'll put 5.00, put another lesser than sign, and then put in the maximum value of that slider. So you can specify all 3 in one line quite easily. So what I've got in here is 0, lesser than 5.00, lesser than 12. And then if I hit return, that will give me a slider going between 0 and 12 with 2 decimal places accuracy, starting at 5. So we're going to use this to control the initial set out point of our grid. So this will control our x coordinate, and we can set the name to do that if we like. Call it x offset. I'll copy and paste that, get another one, call it y offset. And then the next thing we want to do is to have some sliders which will control our column spacing. So again, we're going to set up some sliders to do that. So using the lesser than sign is one way of setting up sliders quickly and easily. Another way of doing it is to type in the start number of your range. So in this case, I'm going to have these sliders going between a range of 9 meters and 12 meters. It's a reasonable sort of standard column spacing for steel frame buildings, at least. So to do that, I'll put in 9.00. Then I'll put a space, and then I'll put 2 dots, 2 full stops, and then I'll type in 12. And this will then set up a slider with 2 decimal places of accuracy running between 9 and 12. So if you haven't seen that before, these are some other means that you can use to quickly set up sliders with the range that you want. So I'll call that one X spacing, and I'll copy that, and I'll call that Y spacing. So these are our 4 parameters that we're going to use to control our grid, and here we've got our input surface. So we've now defined all the inputs we're going to use. Now what we need to do is use those to generate a column grid. And we want a column grid, more particularly, which fits inside this shape. So the first thing that we're going to do is to set up this initial starting point. So we'll do that using the construct point component, as we've used before. It's just a component which lets you specify x, y, and optionally z components of a vector. We use that to create a point. So we'll plug our x offset into x and our y offset into y. That will then give us a point there, which we can control the position of. So that'll be a reference point for the start of our grid. Now what we're going to want to do is to generate our grid lines going in 2 directions. So one way that we could create a grid is through the components under vector grid. You've got a few different options in there, just setting up a regular grid. But if we do that, it's going to be quite difficult then to fit that back onto our surface. So what we'll do instead is we'll go to the Surface tab, and then is it under Analysis? Can't quite remember where it is. Well, let's search for it. I want to find a component called Contour, and that has as an icon a little rectangle with red lines across it. And what Contour lets you do is to take a surface. In this case, it's a planar surface, but it doesn't have to be. It could be any type of surface, and it lets you essentially contour it. So at regular spacings, draw a curve which represents a contour around that surface at that level. So if you drop one of those down, the inputs here are, first of all, S, the breadth or mesh to contour. And surfaces, if you recall, can be plugged into breadths. So we'll use that. The next one is the contour start point. So we'll use that origin point that we specified, put that into P. The next one is the contour normal direction. So this is the direction in which it's going to space out these contours. And by default, that goes to 0, 0, 1, so in the Z direction. So if you did want to have a kind of if you had a topology map, say, and you wanted to generate contours from that, then you could keep that as it was, plug that topology into it, it would generate a contour map for you. In this case, however, we want to use this to do our X spacing, and space out our grid lines in that direction. So we'll go to vector. Under the vector group, we'll find the unit X vector component. We'll plug that into N. And then finally, that last input there is the distance between contours, and we'll plug our X spacing slider in there. So you can hopefully now see that we've got a set of lines drawn across that surface, regularly spaced in the X direction. So that's one set of our grid lines. We'll now want to do exactly the same thing, but in the Y direction, and using this slider. So just repeat that process. Find contour component. Oops, helps if you can spell. Plug the start point in there. Plug the surface in there. Plug the point in the second one. This time, for our normal direction, we want to go back to the vector group, pull out the unit Y instead of the unit X, plug that in there, and then plug our Y spacing slider into D. So we've now got a nice regular grid that we can move across that surface, and that we can adjust the spacing thereof. So this gives us our grid lines on our floor plate. Now what we want to do is to, based on this grid, generate our column positions. So we're going to work in 2D, so we're just going to use points to represent our column positions. And we're actually going to create columns based on 3 different rules here. So the first rule that we're going to use is the fairly obvious one. We're going to create points to represent columns at the intersections between these 2 sets of grid lines. So where these 2 sets of grid lines cross each other, we'll put a column there. It's what you normally do in a column grid. So in order to do that, we need to find the intersections between that set of curves and that set of curves there. So to do that, we'll go to intersect, physical, curve, curve. So this curve-curve intersection component is a very useful component, but it's one that can be quite difficult to use correctly, which is why we're kind of focusing on it today. Essentially what it lets you do is to plug a curve into A, a curve into B. It'll find the intersections between those 2 curves. However, this is a component where you have to be very mindful of Grasshopper's data matching rules, the way that it matches stuff up, the way that data trees work, all that kind of stuff. So you've had a good primer and all that sort of thing, so hopefully this won't be too difficult for you to understand, but it is a little bit counterintuitive sometimes. So what we'll do is we'll pull our first set of grid lines into A and our second set of grid lines into B. And here you can kind of see what I'm talking about. It hasn't found all of the intersections that we might want it to find here. And that's because of the standard Grasshopper data matching logic. So what it's done here is it's matched up this first grid line with that first grid line. That's going into this component as a pair. It's finding the intersection between those 2. It's then matched up that second grid line with that second grid line. It's then finding the intersection between those 2, and so on and so forth, until we get to the end here where it runs out of grid lines in one direction. It just keeps using that one. So again, standard data matching rules, covered them many times. Here they are in application. What we want to do is to get Grasshopper to override those and to instead find all of the intersections between all of these grid lines. So in order to do that, we will first take one of these outputs, the bottom one. We'll right-click, we'll go flatten. So that will then remove the branching data structure from here. So by default, when it comes out of this contour component, each grid line that it creates will be on a different tree branch. So it's keeping the output of each contour separately. So that partially solves the problem. We've then got more points, but we still haven't got all of them, and that's because when we look at the output of this first component, sometimes we're getting branches there which have one item in, n equals 1. Sometimes we're getting branches out where we have 2 items in. And that's because as we cross over, say, this void here, that contour there is actually giving us out 2 separate curves. So while this has partially solved our problem just by flattening this one, what we also need to do is to right-click on that output, go to Graft, just to make sure that every output we're coming out from here is coming out as its own separate branch. So when we graft it, each individual item in each sublist will get its own branch, and we can then make sure that every individual item from this output is being treated separately and is thereby being matched against every single item here. So we can then get out all of our intersection points. So this gives us our basic arrangement of columns inside there. And we can play around with that and try and get it to fit as closely within that shape as we want. But probably what you'll find as you do that is that it's very difficult to actually use only these points as your columns, because you'll end up with situations like this, where if this grid represents our sort of primary steel frame, we're going to have members sticking out here, cantilevering out with no support at the other end. And if that's a very short cantilever, then that's probably okay, I'm probably all right with that. If it is longer than a certain amount, however, we'll probably want to put another column at the end to pick up that support. Otherwise, we'll have ridiculously long cantilevers. That will be driving our structural depth. Our beams will get deeper and deeper, and no one will be happy. So in situations like these, where we've got a very long cantilever coming out the end there, we're going to want to put another column at the end of that grid, wherever it intersects with the edge of this surface, so with the edge of the floor plan. So then these will be our support columns. But we don't necessarily want to do that everywhere. So where we've got very short cantilevers here, it will be kind of a waste of time to put in another column right on the edge there, which was only a few hundred mil away from the column we already had. Because if it's a very short cantilever, then it can probably withstand that without necessarily needing to be deeper than our spanning beam in the middle. So provided it's not going to be driving our structural depth, we're usually okay with having a little bit of a cantilever. So what we're going to do is we're going to look at each of these spans here. We're going to look at the length of that span. So in particular, we're going to be looking at these edge pieces here where it's cantilevering. And if that length is greater than a certain value, we're going to put a column on the end. So the first thing we need to do is to pull out the parts of this that we're interested in. So in that case, it's these end pieces here. So we've got our initial set of contours here. We've got the intersection points between them, and it's giving us the points there. But what it's also doing is it's giving us the parameters on those curves of those intersections. And this is also very useful because we can then use that to perform other operations on those points of those curves. And in particular, what we're going to want to do here is to split up these curves based on those intersection points. So we can do that using this component here under curve division called shatter. So find that component, pull it down. And what we can put in here is our curve to trim, C. So we'll give that our set of contour curves. And what it also wants is the parameters to split that out. So if we give that the parameters along the curve, so if we give that a list of parameters along that curve, it'll split up the curve in between those points and give us out those individual pieces. And this is very, very useful, very, very often in Grasshopper. So we've got here our set of parameters on our set of curves A, TA. So we can use that in order to split up these curves. So we can take that and we can plug that into T, and it will then start to split those curves at those parameters. And we might look at this now and think, okay, that looks lovely, everything's working fine. But in fact, in this case, everything won't be working fine. But in order to see why, we may need to actually bake out these curves, just so we can actually see which are separate objects and which aren't. So I'll create a new layer just to bake these onto. And then I'll right-click on that component, go to Bake, put it on that layer. And then if we select those, we can see that it's not quite working as planned. It's splitting it up in some places, so right on the end here, but not everywhere. And the reason for that is that the branching structure which is going into C is not exactly matched by the branching structure that's going into T. So what we want to have is each curve going in as a separate branch, and we have that. But what we also want in there is all of those T values relating to each one of those curves going in to that second input in a matching tree structure. So we want to have a branch with one curve in it and a matching branch which has however many intersection parameters is being produced for this component here. However, the way that this component here puts it out, so that you can kind of interrogate this data and go into it, is if we look at the branching structure here, what it's doing is it's taking the original branching structure of A, and then for each object in B, it's creating a new branch to store the intersections with that curve separately. So here we've got 3-level branching going in, but 4-level branching going out. So what we want to do is to get rid of that last layer of branching. So again, if it helps, we can use the Param viewer. Right-click, go to Draw Tree, and we can use that to kind of visualize what's happening here. So we can see we have our initial tree, which is kind of our idealized contour curves. Some of those are splitting in two because we have gaps in here. It's creating 2 curves per contour. And then we have, when we graphed it here, 1 branch for each one of those subcurves. And then coming out of TA, we have that original branching structure, but then it's branching it again and creating 1 branch for each item going into B for each one of those input branches. And generally this is useful, but in this case, not so much. So what we want to do is to collapse these outer set of branches. But so that it still matches what's going in here, we still want to retain this inner branching structure. So we only want to actually collapse, we only want to flatten 1 level of this. We don't want to flatten the whole thing back down into a flat list, because then it won't work either. We'll have lots of different cutting parameters on each one. So to achieve that, rather than using flatten, what we'll use is this component here called trim tree. And what trim tree lets you do is, rather than flattening everything, just flatten the outermost set of branches. So if I drop one of those components down in between my inset component and my shatter component, and I can then plug TA into T, So T is the tree that you want to flatten, and this can be any data type, provided it's a tree. And then D here is the number of branches that we want to merge together. So that defaults to 1, and we can leave that as it is. So then by using this component, if we plug that into a param viewer, we can then see that it's flattened out those outermost set of branches, but left those innermost ones alone. So we're then having a branching structure from here, which matches our original one coming out of our contour component. So now if I plug that in there, and then if I delete the objects on that layer, and then I rebake just as a test, what I should now have is each one of those segments coming out as a separate curve. So does that make sense to everyone? Sorry? Oh, in Rhino. You can, well, if you've just done it, then you can press Control-Z to undo it. Otherwise, you can right-click on that layer, go to Select Objects, click on the thing just to make sure it's got focus, and then just hit Delete. Or you could even delete the whole layer itself and get rid of all the objects on it, or something like that. So this is why it's generally a good idea when you're baking stuff out that you might want to replace later to keep that on a separate layer. Okay, so we've now split up those objects in that direction. Now what we want to do is to do the same thing, but in the opposite direction for these curves. So that's what we'll do. We'll get another one of these shatter curve components down. And we can plug our set of curves in there. So we've got our B set of curves going to C now. What we want to do is to put our parameters TB into T in such a way that we have one branch for each curve and one branch for each one of those curves that contains the divisions for that curve. So we want to do the same thing that we did here. Unfortunately, we can't do exactly the same thing here because this output here is structured with respect to A. So the first 3 branches there will match the A input. And the same for TB. So this is giving us our parameters on our B set of curves, but it's giving us it in the structure that comes from A. Does that make sense? So for each thing going into A, we have a separate branch, and then it's creating another set of branches on the end of that for everything coming out of B. So this is where things get even trickier, because what we want to do is to rearrange that data now so that we have something compatible with this. So the first thing that we want to do is to get each one of these curves into its own branch. And to do that, we can just right-click on that input, go to Graft. So now each one of these incoming contour curves will be being treated separately. It will plug in there. If we hover over that, we'll see that now from that flat list, we've gone back to now having each one of those curves in its own little branch. So again, if we try and plug TB into that, then it might appear to be working, but out the other side, I mean, you can tell just by looking at the data structure, we're getting a right old mess, because it's not matching up the right things to the right things. So what we want to do is to take this set of data here, and we want to rearrange it to match this set of data here. And what we want to do, essentially, is we want to keep that last set of addresses. So what we've got here is 0000, 0001, 0002, blah, 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 all the way down to 0405. That last number in that address is the index of the item going into B. So what we want to do, rather than flattening the outside, the last kind of set of branches in here, we want to actually flatten the innermost ones. So we've got everything in a separate branch depending on that last number that we've got in. So we can't use this trim tree component here. Instead, we have to use something else. We're going to have to use this component here, which is very, very useful for manipulating tree structures, because it allows you to do pretty much anything you want. So we'll use this component here called a path mapper. And what this lets you do is to specify a pattern of incoming paths and a pattern of outgoing paths, and it will map from one to the other. So whatever data structure your data is flowing into it as, you can take that data structure, convert it into another one. So you can rearrange all the data and do it in a reasonably straightforward way. So we'll plug TB into that. And if we look at the data structure here, we've got 4 branches in here. If we look at the data structure going in here, we've got 2 branches. We've got 0 and then the number of that curve. So if you double click on that mapper component, up will pop a little form. And what this lets you do is to specify a format for the source data and then specify a format for the output data. And by kind of using consistent references between the two, you can map from one to the other. So to give you an example, what we'll do is we'll put in a curly bracket, because we're defining this as a set of branches. And then we'll type in A, semicolon, B, semicolon, C, semicolon, D. And then close off the curly brackets. So what this is doing is essentially it's labeling each one of those levels of branching in our input list. What we can now do, using those same labels, is to map that into the form that we want. So in this case, in order to match that data structure there going into C, we want to have curly bracket, and then a 0, and then a semicolon, and then D. So what we're saying here is, for each item going into this component, if it's in a form like that, where it's got a set of branches A, a set of branches B, a set of branches C, and a set of branches D, what we'll map that to is a branch with an address 0 and then whatever is in D. So does that kind of make sense? Do you see what we're doing? We're basically telling it to readdress where everything is. So if we then hit OK, going into this, we have a data structure like that, which matches what's coming out of TA. But then coming out of this, we have a much simpler data structure where we're only branching based on the address of D. And if we plug that into T, then we can hover over that and satisfy ourselves that the first data structure is matching the second data structure. So going into C, we have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. Going into T, we also have that same data structure for each one of those lists. And then we can bake that out again and just make sure that we have actually got nice separate objects for each one of those. So the good news is this is pretty much the most complicated thing you'll ever have to do in Grasshopper. This is about as difficult as it gets. So if you can understand this, then, well, you're a lot smarter than I am, because it took me ages to figure this out. So this is the kind of culmination of all this stuff we've been banging on about data structures and trees and how you manipulate them. This is where that kind of knowledge becomes very, very useful in manipulating Grasshopper. And obviously, a lot of the time, you actually need to use a little bit of trial and error and fiddle with it and try and get what you want out. But hopefully this will help to steer you in the right direction. So we now have these two sets of curves here. But actually, there is one flaw in this, which isn't precisely apparent from what I've got at the moment, but if I try and adjust this slightly, I'm not doing it right. It's quite hard to actually find a situation where it happens, but if we have something where, no, it seems like it doesn't actually happen for this one. All right, in that case, we're okay, we can ignore it. All I was going to say is that one thing you have to be careful for this is that when you're splitting stuff based on the intersection parameters, if you are trying to split it and there are in fact no intersections on that bit of the curve, then you won't get an output in here. So one way that you could fix that would be just to pull out the start parameter, so pull out the domain of that curve, and you can do that just by going to deconstruct domain, which is under maths domain. That lets you pull out the start of the domain for each curve, and the end domain for each curve. And then you can just plug those into T as well. And that will just make sure that each curve has its own intersection point, and you will actually get an output from that. So it'll try and cut it at the start. You'll just get out the complete curve again, because if it cuts it at the start, then it will just give you the whole thing. But it's just a way of ensuring that you get all of those bits out. But it looks like in this case, it's not actually necessary, so I won't complicate things unnecessarily by doing that, but if you ever come across that problem using this shatter component, that's one way of getting around it. So we now have our two split up sets of curves. So these represent essentially the beams of our frame in each direction. And the parts of this we're interested in are these outermost parts out here. So the parts where it's currently cantilevering. Those are the bits we want to look at. We want to see how long that cantilever is, and then we want to see whether we need to put a column at that end. So if we want to pull out the pieces at the two ends of this, then all we need to do is to pull that out of the list. So because we're shattering it in this way, the outputs here will be ordered. So if we want to get that piece there, and that piece there, and that piece there, and that piece there. All we need to do is to pull out the first and last items of each list. And I think Connor already showed you this last week. We can do that using this list item component. So we can put one of those down here. We can plug our set of shattered curves into L. So I will default to 0. This will give us out the first item in that list. So if I select that, then we can see that, yes, we're getting all those parts here in this set here, which are cantilevering out like that. If we zoom in on this, we will get these two little plus icons, which let us set it up to give us I plus 1, I plus 2, and so on and so forth, and also I minus 1, which, if our I is 0 and we have wrap turned on, will give us the last item in that list as well. So, might be difficult to see, but if we select that, we can see that we've now got all of the segments in this direction which are cantilevering out, which have some sort of edge near them before they reach another column. We want to do that in both directions. So what we can actually do here is just plug both of those sets of shattered curves into this list component and get both of that. So hold down Shift, plug that second set in there, and out they will come. And you might want to be a little bit careful doing this. And normally, in this case, it works because of the way that we've manipulated this and we messed about with it, we've got different branching structures for these. So these ones coming out here have 4 levels of branching. These ones coming out here have 3 levels of branching. Because of that, when we plug those both in together, they're still being kept in separate branches. If you've got matching data structures, then when you plug them together, the lists in matching branches will get merged together. So ordinarily, this might not be such a great idea, but in this case, it works because of that mismatch of the data structures. So we've now got our set of curves at one end, so at the end of that curve, and set of curves at the start of each curve. And now what we want to do is we want to check the length of that member. And then what we're going to do is, based on that length, we're going to decide what to do. So to find that curve length, we'll go to Curve Analysis Length. So we'll use one of these for these top curves, one of them for the bottom ones. That will give us the lengths of all of those curves. And then what we want to do is we want to say, okay, we've got a certain length under which we're happy for this member to be cantilevering. It's not going to really affect our global structural depth too much. So we'll specify that with a slider. So let's take that as being 3 meters, for example. So we'll put that in as a slider just so we can adjust it if it doesn't look quite right afterwards. And then what we want to say essentially is, if that length is less than that, then do one thing. If it's greater than that, then do another thing. So in coding, this is what's known as an if statement. It's a way of structuring your data flow so that, dependent on what that data is, your program does one thing or it does another. Grasshopper doesn't exactly have that same concept of if statements, but it does still have means of controlling the flow through the program based on what your values are. So the first thing we want to know is that length value greater than that value there? So we want to know, is that the case, true or false? And we can test that by going to the Maths tab under Operators. We've got these components here, larger than and smaller than. And we can use those to test whether one number is greater than another. And if it is, then it will give us out Boolean true. If it's not, it'll give us out Boolean false. So we'll use that larger than component, and we'll say, is that curve length greater than 3? And coming out the other end of that, if we put it in a panel, we should be able to see it, we will have a set of true or false values. So it goes true, 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 false, 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 and so on. So now we can know which of those objects in which branches are greater than that number or less than it. And we'll do the same thing for our start set. So we'll pull down another greater than component. We'll plug that length into A. We'll plug our cantilever limit into B. So I'll rename this cantilever limit. So we've now got a true or false value that tells us whether that particular span is cantilevering too far. Now what we can do is, based on that value, split out the values which are true from the values which are false. And then we can perform an operation on those values which are true and leave the values which are false as they are. So a little bit like in code where you'd say, if a certain condition is true, do this, otherwise do this. This is how you can replicate that kind of workflow inside Grasshopper. And you can do that by going to the sets component. And then, I might be wrong about that. Where is it? Sorry. Under the sets component, under list, there is this component here, which is very, very useful, called dispatch. So what dispatch does is, you give it a list of items, you give it a list of true or false values. For each one of those items, if the matching value is true, then it'll put it out from one output. If it's false, it'll put it out from another one. So it's essentially just splitting off that data based on that condition. So we'll drop one of those down. L is our list to filter. So we'll use our original set of curves here. So coming out from that -1 output, that's what we'll plug into L. And P is the dispatch pattern. So this defaults to true or false, and that will kind of loop round if you don't do anything else. So if you give that a list of data and you don't change that, the first one will be true, the second one will be false, the third one will be true, the fourth one will be false, and so on and so forth. So what it'll end up doing is it'll split out every other one, and that's actually quite a useful thing to do sometimes. But in this case, what we want to do is to plug in the output from larger than. And then what will happen is any of these curves which are longer than this value will come out from A. Any of them which are not will come out from B. And because they're both coming out from the same component, it can be difficult to actually see which is which. But if we plug that into a curve parameter component and we select that, then we can see which ones are true and which ones are false. So we can see, for example, that this member here is longer than 3 meters. That member there is shorter than it, so it's not being selected. And then what we can do finally is we can say, okay, this line at the end of this row of beams is longer than 3 meters, so what we want to do is to put an extra column on the end there. So all we'll do is we'll go to curve, we will get the endpoint component, we will plug that in there, and that will then give us out the endpoint of that curve as a column position. And again, in this case, we only want to keep those endpoints. We don't want to duplicate columns we've already got. So I'll put the E output there into this separate parametric component. And then, so we don't see that stuff, I'll select it all, middle click, disable preview. Okay, so now we've looked at the end spans. We've said, is that greater than this value? The length of that, is that greater than that value? If it is, then we'll put a column at the end of it. Now we'll do the same thing for the start ones. So essentially what you can do is copy and paste this part if you like. Except this time we're going to put this output here into L and this output here into P. So same logic, it's now checking that set of outputs, measuring the length. Is that longer than this? If so, put that out into A. But in this case, because these are the start points of these curves, the endpoint of that curve we want to take as our column position is going to be the start of that curve. So we've built some intelligence into this model now. It's now deciding, based on these criteria that we've given it, where to place columns and where not to. So to keep all of our column positions together, I'll bring down another point parameter component. I'll hold down Shift, and I'll put those two sets of endpoints in, and also way back here at the start, the set of points which are coming out from my curve intersection component. I can plug those all in there, just so we've got all of our column positions so far into that one collection. And at this point, that data flow is no longer relevant to us. We only care about where we have columns and where we don't. So what I'll also do is flatten that down to get rid of the data structure that we've been using so far. Just so this is one nice flat list. So it's coming from the two ends, but also way back over here from your curve intersection component, you want to take the points that that's putting out. So we've got all of these column positions here. Can anyone spot anywhere else where we might maybe want to think about putting a column? I'll give you a hint. So we can imagine that as well as this frame of beams here, we maybe have an edge beam that runs around here to stiffen up that edge. But where we have corners like this, we're probably going to want to put in another column there to pick up that corner and stop that whole thing just sagging down. So what we also want to do, to make sure we're kind of picking up all the parts of this structure that might need support, is we're going to look at each of these vertices and we're going to say, how far away is that point from another one of these columns? So we'll say, from each of these points, look at the closest other column, and if that is further away than our cantilever limit, then we'll put another support point in there as well. Just so we don't have a situation like this where we've got an unsupported corner of our slab. So first thing we want to do is to pull out all of these corner vertices, and then again we'll examine these and we'll say which one of these we want to keep as columns and which ones we don't. So to do that, we'll take our initial surface way back at the start here, and we'll use the deconstruct BREP component from surface analysis. And if we plug our surface into that, this will pull out the faces of that BREP, which is just our surface, because it's only a single surface, it's not a poly surface. It'll give us the edge curves of that BREP, and it'll also give us all the vertices, which is what we're interested in this case. So it'll give us a point at each one of these corners. So we'll move that all the way down the end here, but that's coming from our initial surface. So now what we want to do is to say, from each of these vertices, where's the closest column that we already have? Is that within a set distance? If not, we'll get rid of it, or vice versa. So we want to find the closest point, and what we could do is we could use the distance component to measure the distance between each one of these vertices and each one of these points here. We could then find the shortest one of those distances. We could find the index of that shortest distance. We could then pull out from that list of points that point at that index, and then we could find the pairing that has the shortest one. But instead what we'll do is we'll use this component here, which is just called closest point. And this is quite a useful component. It does a very fast check on a whole bunch of points and tries to find the one from that that's closest to a particular input point. So going into P, we have the point to search from. Going into C, we have the cloud of points to search. So we're going to want to find from our set of corner vertices V, put that into our points to search from, and we want to find the closest point from our list C. And this component is actually an interesting exception to some of what we've been doing in order to kind of manage the data matching. If it was consistent with what we've been doing so far, then what you might want to do is to graft P to get each one of those in a separate branch. But in actual fact, that isn't really necessary in this case. And the reason for that is if we hover over P, it says points to search from, so it only wants a single input there. Going into C, it wants a cloud of points to search, and it says cloud C as list. So it's already taking in that list and treating that as one item, but it's taking in P as a single point. So that means that it's automatically going to match up each one of those input points P with that whole cloud of points. It's just the way that this component works. So when you're trying out new components, always be careful to look for and see whether it says either a single object or whether it says as list, because then it means that it's going to automatically treat all of those objects as one thing. So this will give us out the actual closest points. It will give us out also the distance between P and C. So that will be the distance from each of our V points to the closest one of these points here. So we can then say, we can basically do again what we did here. In fact, we can just copy this part of this definition here. In fact, I won't do that because it'll be confusing. I'll just do it again. So what we can do is we can say, is that distance there, plug that into A, is that greater than our cantilever limit, B? So we'll plug that D output there into A and our limit slider into B. So we're then getting true or false. And again, we can just go to sets, list, dispatch. And then we can plug our list of vertices into L and our list of greater than values into P. That will then separate out the points which are furthest away, that are further away from any of these columns into A, and the points which are within that tolerance from an existing column into B. And we can then use a point parameter component to pick up those outputs and put them in there. So if I turn off the preview for that, and if I also turn off previews for these, we can now see that on some of these vertices, such as there and there, it's further away than our limit, so it's putting in a column to pick up that change in direction. But at positions like here, where it's fairly close to an existing column, it's not. So we've now got, if I just pull them together, all of the column positions that we've generated for this floor plate. So, now comes the fun bit, where we're actually going to use Galapagos to optimize this. So we've built this definition now, and we can play around with these variables here to try and find a nice grid arrangement that we like. And we might find something, or we might maybe find it a bit difficult, because kind of as we're moving one parameter, it's sort of moving one point closer to where we might like it, but it's also moving other points away from it. So it can be a little bit difficult to find an arrangement here which we know is going to be optimal. So this is what we're going to use Galapagos to try and do. And first of all, we need to decide what is an optimal arrangement. What do we care about this arrangement in order to say this arrangement is better than this other arrangement? And there's several different things we could pick here. For the sake of simplicity, what I'm first going to try and optimize based on is the number of column positions. So I want to try and avoid having too many extra columns that I don't need. So for example, around here I've got quite a few columns where I've got a set which is fairly close together, and by manipulating that we could probably come up with a better arrangement which had fewer columns, therefore less obstruction of the space, happier architects, everyone sleeps better. So to begin with, we'll try and optimize this based on the number of columns that we're creating. And in order to do that, I will put all of the column points we've created so far. So those from our grillage, and those from our vertices into one collection. I'll flatten that again just so it's all in one flat list. So one little thing that Grasshopper likes to do to annoy you is that sometimes these things are actually in data structures, but even if they're in a data structure which has only one branch, it won't necessarily display that as a tree. So it'll only show you the double dotty lines if there is a branch in it. But that doesn't necessarily mean that it's in a compatible data structure. So for example, here we've got two flat lists coming in, but if we hover over that point there, we can see that one of those has come in as one branch with just an address of 0. The other set has come in as another branch with an address of 0, 0, and because they're in separate branches, as far as Grasshopper is concerned, it's not merged then, which maybe you assume it would have done. So again, we'll just right-click and flatten that, and then we will go to Sets, List Length, and we'll use that to count up the number of columns that we currently have. So we've got 42 at the moment. So we've got 42. We could drag this panel back over to the start, and we could play around with these sliders and try and minimize that number of columns. But why have a dog and bark yourself? What we're instead going to do is use Galapagos to do this for us. What Galapagos can do for you is it can take control of a number of sliders in your definition and try and manipulate those until a particular output number, in this case the number of columns, is either maximized or minimized. So Galapagos you can find under the Params tab, under Util. There it is, called Galapagos. And we can drop that down onto our canvas. And this is a bit of a funny looking component. It doesn't work the same way that any other components work, really. It has two sort of inputs. It's got a genome and it's got a fitness input. And the fitness, quite unusually, is sticking out the bottom. So the genome is essentially the set of sliders that you're giving it and allowing it to control. So you can drag out from that and snap onto a slider. So in that case, I put it on the X offset. So you can drag that out and connect it to a slider. By default, it'll only allow you to put in one genome, but generally speaking, that's not particularly useful. So we'll hold down Shift, and that will then let us to specify several different sliders that we can use in order to do this. So by doing that, Galapagos will be controlling all of those sliders. What we next want to give it is the fitness. And what the fitness is essentially a score that you're giving that particular combination of parameters that lets Galapagos know how good it is. So our fitness score in this case is going to be the thing that we want it to minimize, which is going to be the number of columns. And you can drag out from that and try and attach it on something. It's a little bit finicky about the types of components it will attach to, so it won't, for example, attach to this panel. But if I drag down a number param component, plug that in there, then I can attach that to that component. So we've now set this up to optimize this value here by manipulating those sliders. To actually set it running, what you need to do is to get Galapagos and double click on it. Up will pop the Galapagos editor. And this has got several different tabs in it. This first tab here that will come up when you first double click on it gives you a set of different options for how the solution is going to be run. We'll come back to these in a little bit later. The only thing we want to adjust here is this first option here, which is called fitness. And this basically tells it whether it wants to try and find the maximum of that fitness score or the minimum. So its defaults to maximize. We're going to decrease. We're going to click on the minus, instead set that to minimize. So it's going to be trying to reduce the number of columns. Once we've done that, we can go into solvers. The Start Solver button here is what we're going to be interested in, but before we do that, just click on that button there. So this option over here is essentially a display option. It just tells it how often you want to see the results. If you put it on this option here on the left-hand side, what that means is it will show you every single combination that it's trying. So in this case, we want to see what it's doing, so we'll put that on. By default, it'll only show you the last best option that it found. But we'll put that on there for now. And then if we hit Start Solver, we can set it running, and we can see what happens. So to begin with, it was juddering all around the place. It was shaking it up. It was trying to find a decent set of options. And now, as time's gone on, it's gradually optimizing that. It's gradually trying to find better and better and better results until it finds a better arrangement in here. So while that's running, it's probably worth just going through what exactly it's doing and what exactly a genetic algorithm is. So a genetic algorithm essentially tries to replicate the process of evolution through natural selection that exists in biology. So what it's trying to do is it's trying to evolve solutions in the same way that organisms evolve from simple, less optimal forms up to far more complicated, more optimal forms that better suit their surroundings. So if you understand the process of natural selection, it's going to be very helpful here because it's essentially the same thing, just modeled in a computer. So the first thing that it will do is it will randomly generate an initial population of different options. So it'll say, okay, I'll set one set of random slider combinations here and another one like that, and so on and so forth. So it'll do that a certain number of times, say 50 or 100. It'll generate a set of options. What it will then do is it will score those options based on the fitness function that we've given it. So that fitness score that we've given it, which in this case is the number of columns, that will essentially be the score for each one of those options. And that determines how good, essentially, that option is compared to the other ones. So it does that a certain number of times. It gets a sort of a population of different solutions, initially just generated completely at random. It's trying to kind of cover as much of the solution space as it can. And then what it does is it looks at that population, it pulls out the best one of those, essentially survival of the fittest. So the better that score, the better the percentage chance that particular combination has of surviving. It takes that set of surviving members and it breeds them together. So if you've got one set of slider values and another set of slider values, it'll produce a new mixture of those slider values, which is essentially the offspring of those two options. So it'll create a new option similar to, but not the same as those ones. And then what it does is it mutates them. So based on a percentage chance, it will take those values and it will tweak them slightly. So they won't necessarily be exactly what you might expect from a straightforward merging of those two answers. It will put in a little bit of randomness in there as well, just so there's some variation still going on. And then essentially what it does is to repeat that process. So at each stage, it's taking the best ones, breeding them together, mutating the offspring, and then for that new set, culling out the worst ones, putting on the best ones. So the idea is basically at each generation it's pulling out those best options. It's doing that over and over and over again. So as time goes on, your solutions are getting better and better and better and better. So in pretty much the same way that it works in the biological world, so too it works in Galapagos. So it'll keep going until it reaches an end condition, and usually that end condition is, it'll find the last best option that it found, and then it will keep going for a certain number of tries. So in this case, I think it's set to 50. So it'll find the best option. It'll keep going for 50 more generations. And if it doesn't find a new optimum within those 50 generations, then it will give up, and it will say, okay, I've probably found the best one that I can. So here we've reduced that number of columns down to 33. And I'll set it running again, just to go through this interface here. So this graph here, which is sort of drawing itself as we go along, that is showing the current range of fitness values. So as time goes on, as it's decreasing the randomness of it, it is gradually reducing that randomness as well. This plot down here kind of shows how genetically similar each of the current options is. So sometimes you might see this kind of splitting off into two groups, where you've got essentially two competing types of solution coming to the fore. This graph here is just a straightforward plot of your slider values. And then this section over here is showing each, it's kind of the top scoring options. So it's not finding any better than 33. So if we want to see what those options are exactly, we can click on any of those and find them. So what's nice about this is that you can essentially apply it to any type of problem you want. All you need to be able to do is to express how good a particular option is as a score. So in this case, what we're trying to do is to minimize the number of columns. So our score is our number of columns. But in fact, this isn't really a very good fitness score to take for this. And that's because it only varies in whole numbers. So in order for Galapagos to work best, it needs to know whether one option is slightly better than another, or whether it's slightly worse, and so on. So if it's jumping from 33 columns to 34 to 35, there's a bit of a range in there of different options which may be better or they may be worse, but that kind of information is being lost. So this is a sort of a simple way of doing this, but it's not necessarily the best way of doing it. But what we can do is we can pick another way of describing that fitness. So maybe instead of the number of columns, what we're interested in is the minimum spacing between two columns. So we want to make sure that we don't have two columns which are too close together, which is going to kind of block off our flow, and probably not make an architect happy with us. So what we could do is to look at all of our points and find for each one of our points the closest one of our other points, so as we've done here already, but this time looking at all of those points. So again, we will go to vector. We will use this component here, closest point, we'll plug all of our column points into P and all of our column points into C. In fact, we won't do that because that's a bad thing to do, because then all of our distances will be 0, because every point will be looking at this and it will be finding itself in that list, so the shortest distance will always be 0. So instead what we want to do is we want to compare every point that's in this collection to every other point excluding itself. So to do that, we will go to sets. We will take this component here, which is item index. So what we'll do here is we'll take each item, we'll find the index of that item in the list. So we'll plug our list of points into L and our list of points into I. This will then give us the index of each one of these points in its own list. We can then use that index to cull out that item from that list. And we're going to need to use a little bit of tree manipulation here as well. So we have this component here, which is cull index, and that lets us use that index to trim out an item from that list. So our list here will be our set of points. Our culling indices will be our outputs here from the index of that list. That will then, in that list, find that index and remove it from that list. And in this case, because this is all a flat list, we will end up having nothing coming out the other side. What we'll do instead is we will go to I and we'll graft it so that then each one of those culling indices is being treated separately. And then what we should find is that coming out of L, we have a whole bunch of different sublists. Each one of those will have a different index removed from it. So for the first point, we'll have a branch in there which contains all of the other points apart from that one. For the next one, I have the same thing except for that point. So we can then use that in order to find our closest points. So if we plug that into C, and then we likewise graft P, so then we'll have one branch. We'll have one branch in P for each one of our points, and one branch for C, which contains all of the points other than that point in that list. And then coming out from D, we should then have the distances from each of those points to any other point. Does that make sense? I take that as a yes. So we've now got our set of distances coming out from D. What we want to do, so we've got a whole bunch of numbers here. Unfortunately for Galapagos, what we need to do is to give it one single number. So we can't just plug in this whole list and expect it to work. It just needs one number which it can use to describe that particular option. So what we'll do is we'll find the minimum of all these values. So to do that, we'll flatten that list. That'll give it to us all in one nice flat list. And then from those values, we want to find the smallest one. So to find the smallest item in a list, you might think that this minimum component here looks very nice, but in fact, it doesn't. all this component will allow you to do is to put in two numbers, and it will tell you which one of those two numbers is the minimum. In this case, we want to give it a whole bunch of numbers and find the minimum of that whole list. So instead what we'll do is we'll construct a domain around that list using this component here, bounds. So this is under maths domain. If we plug our set of values in there, out from the other side we'll get a domain which describes the limits of that list of values. So we'll get the smallest value to the largest value. So in this case, we've got 1.95 to 11.2. But we can't give Galapagos a domain, it wants a single number. So what we'll then do is deconstruct that domain, which will give us the start and end values of that numeric domain, and the start value there will be our minimum value. From which one, sir? No, because that will only give you it as a domain. It might actually be possible. I haven't tried this recently. Let's see. No, so I thought it might be possible to just plug that domain into a number component and it would give you the minimum, but in fact what it gives you is the length of that domain. So don't do that, it doesn't work. But it's worth a try. So now we've got the minimum value coming out here from the start of our domain. So I'll put that into a panel, and I'll pull that all the way back to the start again. And then if I plug that into this number here, which we're using as our fitness score, we can then rerun that using this as our fitness score instead. So this should be slightly better because it's not actually got these fixed set of points. It can actually give it a bit more guidance on whether one option is slightly better than another or not. So now we can rerun that again. Before we rerun it, however, in this case, our heuristic is slightly different. Instead of wanting to minimize the number of columns, we're wanting to maximize the spacing between them, or the minimum spacing between them. So we'll set that to be maximized instead. And while we're here, we'll go through these other options on this form. Just below that, you have a threshold. And what you can do is to put in a particular value there. And once it's reached that value as a fitness score, it will stop going. It'll say, okay, I've reached a score which is good enough, and it'll cease operation then. Another way of stopping it is to toggle on this runtime limit here, and then you can just leave it running for a certain amount of time. So it defaults to an hour and a half. And then after that period of time, it'll stop. The way it normally does it is based on this input here, which is the max stagnant number of generations. So that defaults to 50. So what that means is, after it's last found a new best option, it'll keep going for 50 generations, trying to find a new one, and then it will give up. The population here is the number of individuals per generation. So that's set to 50, so for each generation it will be trying out 50 different solutions, and then it will be picking from them the best set, going into the next generation, which will likewise have 50 individuals in it, and so on and so forth. The exception to that is the very first run. So in the very first run, it's going to be generating a completely random set of variables, and it wants to make sure that it's got good coverage of that solution space. So because it's random, you might end up with all of your points, kind of all of your sort of all of your possible range of values being in quite a small subset of the possible range, just sort of purely through chance. So what this next input here does, the initial boost, is it say, okay, multiply that population by a certain factor for the first run. So by default, that's 2. So the very first time when it's just generating completely random options, it'll multiply 50 by 2, give you 100 options. It just kind of reduces the odds that it's going to miss a little pocket of kind of optimum solutions, just because it hasn't covered enough of that space. So maintain is the number of individuals that it sort of carries on for each generation. And then inbreeding is the kind of factor of where it's choosing pairs from. So if that's 75%, then 75% of the time it's going to be choosing a mating partner for each one of these from fairly close to its own solution space. And then this last bit here is for another solver, which we won't cover in too much detail, so we can ignore that. So now that we set that up, we can go in here, we can hit Start Solver again. If I put it on Displayable Genomes again. So now it will keep running, and it will try and solve it for that different fitness score. So now it's trying to maximize the spacing between columns. So you can see, for example, that whereas here we used to have 2 quite close together, now it's naturally trying to position that midway between these 2 points to give a slightly nicer arrangement. Incidentally, each one of these little white boxes on here is a point where it's found a new best solution. So that each one of those is where it's last found the new best solution. It's going to keep going 50 generations after that point, or until we stop it. So this can be quite useful in order to kind of try and generate optimum arrangements of particular things based on parameters you've set. However, I've used these kind of things quite a few times in my career, but I've never actually ever taken pure outputs of an optimization process and then just built it. So it's a little bit of a misconception that that's what optimization is for, in my opinion. Lots of people kind of think, right, I'll run an optimization algorithm, I'll get the optimum, and then I'll build that. But that's generally not the way things work in practice. The use of these things is not necessarily to give you an optimum, because in real life situations, what exactly constitutes an optimum is not always something that's very easy to describe. And it's not always something that's very easy to set out using rules. So what might be the optimum for, say, a structural engineer is unlikely to be the optimum for an architect or for a building services engineer or for somebody like that. So there's always going to be a little bit of fuzziness around what exactly that optimum means. There's going to need to be a little bit of to and fro and discussion and so on and so forth. But what this sort of thing is very useful for is for guiding the process of exploration. So it's never been the case in my experience that you can just say to the computer, okay, here you are, go off and design this, but you can use the computer as part of that design process to help steer your own understanding and your own development of the problem. So for example, here, I'm specifying that it has to give me a regular grid, so that's what it's trying to give me. In real life, however, there might be ways that I might want to deviate from that. So I might look at this and I might say, well, that's sort of almost towards that edge, so if I just slightly adjusted that and if I slightly went off of that regular grid, I can maybe come up with a better arrangement. So optimization programs like this, and even sort of stuff like automating beam sizing, very often you'll want to apply some sort of engineering judgment to the results of that as well. So for example, I've done beam optimizations where it just churns out and it gives me the optimum beam size for each individual member in a building. But if you were just to give that to a contractor where every single beam was a different type, you probably wouldn't be too happy with that. So then you need to apply a little bit of common sense to actually kind of reduce those into a certain number of groups and so on and so forth. So here it's sizing based on position from columns. It's going to keep going for a while. It's finding some quite nice sort of open gaps here. As I say, in real life, things are often more complicated. So you may want to just apply your own judgment to it, but you can also build more and more complications into these models. So you don't need to just size based on a single criteria. So you need to optimize based on a single number, but that number doesn't necessarily need to be comprised only of one aspect of the design. So, for example, if I stop this, what you might want to do in your optimization is take account of both the number of columns that you have and your column spacing. So you might say, okay, I want to reduce the number of columns, and I want to make sure that they're as far apart as possible as a minimum. And you can do that simply by coming up with some sort of equation which describes both of these together. So for example, what we might do is say we want a certain number of columns and we want that to be minimized. We've got our spacing and we want that to be maximized. So what we could do is to get a subtraction component, and we could take away from our number of columns our spacing. And that would mean that as our number of columns was decreasing, our score would go down, and also as our spacing between columns was increasing, our score would be going down. So we could then minimize that combined score in order to come up with a solution that respected both of those criteria. So you can come up with quite complicated fitness functions built up from several different criteria. So say you wanted to have an area in here which was column free. You could maybe sketch out an area and then check whether any columns were in that zone. And then if there were, then apply to that score a big penalty. So you can say, okay, I want to minimize the score, but if there are any columns within, say, a zone around there, which is my main entryway, then I'll give it a big penalty to that score to let it know that that's not a good solution so far as I'm concerned. So you can really try and build in lots and lots of different parameters into this and build up more and more complicated solutions. So if I run this again now, and I set it to minimize, then now when I run it, it's going to be trying to minimize the number of columns and also maximize the spacing at the same time. So in this case, the number of columns is going to have a larger impact on that score than the spacing would. So that's going to have more of an influence on the design, perhaps. So maybe I'd want to factor up that distance so that it was then having a larger thing. So I'd want to multiply that distance by a certain number so that the influence each one of those values was having on the overall fitness score was balanced out. So it's possible to express quite complicated things here. You often have to kind of play around a little bit with how you're building these equations, how you're factoring stuff so that you get the result that you want. And so kind of Galapagos is giving you options that you think is going to be good. So I'll leave that running for a little while, see what it comes up with. And while that's doing, I'll show you some other examples of how this is used in practice. So this is an example we've just covered, optimizing a column grid. But as I say, this is actually quite a flexible methodology that you can apply to any sort of problem. So this is a video from about 6 years ago, actually, which is somewhat depressing. And this is using Grasshopper and Galapagos and a plugin that I wrote called Salamander in order to optimize a truss. So the geometry generation side of this is very similar to what you did with Vincenzo in order to create a truss. What is then happening here is extra data is being assigned to that in Grasshopper, so it's giving it section sizes and it's giving it loads and restraint conditions and so on. That's then being exported out to GSA for analysis. And the fitness score then is based on the results which are coming back from that analysis. So in this case, I was trying to minimize the weight of this truss while also ensuring that the stresses in that truss didn't exceed the capacity of the steel. So essentially the fitness score here was built up based on the overall mass of the truss, and it was adjusting the dimensions and the geometry and the sizes of the members in that truss in order to do that. And then the lighter that truss, the better, but if it was exceeding at any point a limit on maximum stress or a maximum deflection, then a penalty was being applied to this to let it know that that wasn't a valid solution. So essentially what it was doing at the end was it was trying to find the lightest solution it possibly could that still fit within those limits. And in this case, it's just working on a single truss. The part going out to GSA and reading back again was reasonably slow, so I've actually cut some bits out of here. It actually took about 20 minutes. But it came up with a reasonable solution in the end that was a reasonably lightweight option. So that was just for a single truss. I have actually done this on a whole roof of a sports hall, which it can do. It can handle that, but the more parameters that you give it to control, the longer it's going to take, kind of exponentially, if you like, because the more dimensions you've got in your solution space. So to do a whole roof with this, I had to basically kind of leave it overnight, go away, come back in the morning, and hope that it hadn't run out of memory or crashed or anything like that. So it's not necessarily ideal for that sort of structural solution. For actually sizing things, there are better optimization algorithms available, but it is quite a handy solution in the fact that it's built into Grasshopper. It's quite easy to just plug it onto the end of an existing definition, and it's also pretty flexible in what you can do with it. So this is something else that I've done a bit more recently. This is a bit more straightforward. This was examining sort of building massings on a particular site. And I can't tell you where this site is or what the project was, but one of the key constraints of this was that underneath it were running 2 underground train lines. So something that we wanted to look at quite closely was how much load was being put onto the ground over those 2 train lines. So in this case, Galapagos was generating different framing options for this building, different kind of massing options, different heights here and there. It was then doing a rudimentary load takedown for each one of those columns, and plotting that out so we could see what the forces being put into the ground over those positions were, and then it was trying to optimize based on that. In a similar sort of thread, in RCD, a while ago before I got there, a bit more sort of general research has been done, which we're now going to be picking up again and pushing forward on building massing, using genetic algorithms to generate different forms and then assessing them for various different criteria. So things like sunlighting, kind of wind comfort, things like that. We can use Galapagos to generate different arrangements of the building, test them out for these criteria, and then optimize the overall building arrangement to give an architect some feedback on that kind of thing as part of that process. So you can kind of get Galapagos, if you like, to design buildings for you. And Galapagos is nice because it's built into Grasshopper, but there are other options available. So there are 3 different optimization plugins which work in a similar way that I'm aware of. There might be even more. There's Octopus, which is similar to Grasshopper, but it does actually allow you to put in multiple fitness variables, and it will kind of keep track of those independently. So you can then afterwards kind of adjust to fit the balance that you want. Opossum is slightly different. It uses machine learning to try and find the optimum solution, so it's a slightly different algorithm. You also got Goat. I'm not entirely sure what that does, to be honest. I've never actually used it. But yeah, there's different ways of optimizing stuff that you can try out in Grasshopper. And my illustrious predecessor as head of RCD, John Harding, he now works in academia, and he's currently developing something called Biomorpher, which is a kind of interactive way of generating genetic algorithms. So as well as generating these different options, you can then have some input on which direction it's going in. You can pick the option that you like, and it will generate new forms based on that for you. So that, I think, is... Oops. That's the end of the session today, with 5 minutes to spare. So if you have any questions about that, then feel free. I think next week, Vlad is here. He's going to be showing you Karamba and how you can do structural finite element analysis inside Grasshopper itself. And then the week after that, I'm back again to talk to you about scripting. So if you're not sick of me already, then you will be by the end of that week. So if there are any questions, feel free. Otherwise, I will see you in 2 weeks, and Vlad will see you next week.